What if the very carbon dioxide we're desperately trying to reduce, the heart of the climate problem, could actually become a key part of a new sustainable economy?
Hmm.
What if we could literally pull CO2 out of the air and turn it into fuel for planes, ships, vital
It
industries?
sounds pretty radical, doesn't it? Almost like science fiction.
It does.
But that's exactly the possibility we're digging into today. This idea that CO2 isn't just waste to be buried, but potentially a really valuable raw material for the future.
Welcome to the deep dive. We're here to give you the essential insights from crucial research shaping our world. And today, well, we're tackling a really pivotal study. The full title is Global Demand Analysis for Carbon Dioxide as Raw Material from Key Industrial Sources and Direct Air Capture to Produce Renewable Electricity-Based Fuels and Chemicals.
Quite a mouthful.
It is. But our mission here is to cut through the complexity and pull out the key takeaways for you.
And the context, the big picture challenge is crystal clear. Climate change is, well, it's the challenge. We absolutely need what researchers are calling defossilization.
Defossilization,
Yeah.
moving away from fossil fuels entirely.
Exactly. It's a huge systemic shift. Not just trimming emissions, but replacing those old carbon cycles with new renewable ones. We need true carbon neutrality to hit that ambitious 1.5 degrees Celsius target.
Right. So the big question guiding us today is, as we push towards 100% renewable energy, how much CO2 are we actually going to need as a raw material? And maybe even more critically, where on Earth is all that CO2 going to come from?
That's the core of it.
Okay, let's unpack that first part. Why is CO2 becoming this hot commodity all of a sudden?
Yeah,
It seems to come down to those industries that are notoriously hard to clean up directly.
precisely. The hard-to-abate sectors, as they're often called.
Like what specifically?
Well, think about long-distance transport, shipping, aviation. They need fuels with a really high energy density.
Right, you can't fly a jumbo jet across the Atlantic on batteries. Not yet, anyway.
And not even close with today's tech.
Yeah.
So this is where something like e-kerosene, a synthetic jet fuel made using renewable energy and CO2, becomes a potential game changer. It's a drop-in replacement, basically.
So same planes, different fuel source.
Potentially, yes.
Wow.
Maintaining how things work now, but slashing the net emissions.
Oh.
And it's not just transport.
No.
Think about heavy industry. Processes needing super high temperatures or specific chemicals as building blocks, feedstocks.
Okay.
For those, you could use e-chemicals like e-methanol or e-methane to replace the fossil-based versions.
So define these terms for us simply. E-fuels, e-chemicals. What are they, really?
They're essentially synthetic twins of fossil fuels and chemicals. But, and this is the key difference, they're made using renewable electricity, think solar, wind, and captured CO2.
So the carbon comes from CO2 that's already out there, not from digging up more fossil fuels.
Exactly. It creates a loop. You need carbon to make these fuels and chemicals, so where do you get it sustainably? That brings us to CCU and DACU.
Carbon capture and utilization.
Right, CCU, capturing CO2 from places like industrial smokestacks, and DACCU.
Direct air carbon capture and utilization, pulling it straight out of the ambient air.
Yep. So you capture the CO2, use it to make your e-fuel. Someone burns that fuel, releasing the CO2.
Hmm?
But then you capture CO2 again, maybe from the air, maybe from another source, and start the cycle over. It's aiming for a net zero loop.
Okay, so just to lock this in. This study is looking at the demand for CO2 for these e-fuels and chemicals in a future running on 100% renewables. And it's figuring out the potential supply from specific industries and from pulling it directly out of the air.
That's the map it's trying to draw, a potential blueprint for this circular carbon economy.
All right, let's get into the numbers, because the projected demand for CO2 in this study, it's pretty eye-opening. We're talking serious growth.
The figures really are striking. In 2030, the study estimates global demand for CO2 as a raw material at around 0.6 gigatons a year. Seems like a lot, but fast forward just 2 decades to 2050. That number jumps to 6.1 gigatons per year.
Wow, okay, that's a tenfold increase.
A tenfold increase. It really highlights the massive scale-up needed for this kind of transition. It's not gradual, it's exponential.
10 times more CO2 needed as feedstock in just 20 years. So who needs all the CO2? Which sectors are driving that huge increase?
Well, initially it's the chemical industry. They're projected to be the biggest users early on.
Yep.
In 2030, something like 98% of that CO2 demand, mainly for making e-methanol.
Okay, almost all of it at first.
But here's where it gets interesting. While the amount of CO2 the chemical industry uses keeps growing up to maybe 2,800 megatons, by 2050, its share of the total demand actually drops, down to around 46%.
So other sectors must be catching up, and fast.
Exactly, like the power and heat sectors.
How do they fit in?
They start pretty small, maybe 2% of demand in 2030, just over 10 megatons. But by 2050, their share jumps to 18%. That's over a billion tons, 1088 megatons.
What are they using it for?
Mostly for e-methane, especially for high-temperature heat in industry. Think furnaces, kilns, places where it's easier to swap the fuel than rebuild the whole process, especially if you can reuse existing gas pipelines.
Right, leveraging existing infrastructure. Makes sense. Okay, but the really explosive growth, the one that probably connects most directly for people listening, that's transport, isn't it?
That's where the curve gets steepest. In 2030, transport demand is tiny, almost negligible, less than half a megaton.
Less than 1%.
Right. But remember those hard-to-abate sectors? Marine shipping, aviation.
Yeah.
As they face pressure to defossilize, maybe through regulations or just fuel costs, the demand for CO2 to make their e-fuels, like that e-kerosene we mentioned, just explodes.
How much are we talking?
This study projects transport will need almost 2,200 megatons of CO2 by 2050.
Wow. From almost nothing to over 2 gigatons.
Exactly. And the really sharp climb is expected in the 2040s. That decade looks critical for decarbonizing long-distance travel and shipping.
So let's pause there. What does this mean for you listening right now? These aren't just abstract gigatons. This huge growing need for captured carbon is directly linked to the future of flying, the future of global shipping, how we make steel, cement, plastics, countless things.
It signals a really fundamental shift in the industrial backbone of our world. It could affect everything from the price of your plane ticket to the cost of goods shipped from overseas.
Okay, so that's the demand side, huge and growing fast. Now, where does all this CO2 actually come from? This study looks specifically at what it calls sustainable and unavoidable industrial sources first.
Right. The idea was to find CO2 emissions that are really hard to eliminate, even if the energy used becomes totally renewable.
So what qualifies?
Three main ones. First, cement mills. But specifically, the CO2 released from heating limestone, the chemical process itself, not from burning fuel to heat it, because that heat energy will come from renewables eventually.
Okay, process emissions from cement. What else?
Second, pulp and paper mills. They release bio-CO2 carbon that trees recently absorbed from the atmosphere, so using it as part of a faster cycle.
And third?
Waste incinerators. Capturing the CO2 from burning municipal waste. Again, it's dealing with the waste stream that already exists.
And this study was quite picky, wasn't it? It deliberately left out some major CO2 sources.
Very picky, and for clear reasons. It excluded things like fossil fuel power plants because, well, the goal is to replace those entirely with renewables so their emissions are avoidable.
Makes sense.
It also excluded most other biomass burning, often due to concerns about sustainability or the high cost of capture, and things like traditional steel plants and fossil fuel refineries, because they're expected to be phased out or fundamentally changed in a defossilized world.
So it's really focused on CO2 sources likely to persist even in a fully renewable future.
Exactly, the unavoidable ones.
And these sources, these unavoidable industrial emissions, can they actually meet that early demand?
They can make a really big dent early on. The study estimates that by the 2030s, these specific industrial sources could potentially supply around 2.1 gigatons of CO2 per year.
Which covers the 0.6 gigatons needed in 2030 pretty easily.
Comfortably, yes.
Yeah.
It provides that crucial initial supply, acting like a bridge, while other technologies like direct air capture get up to speed.
Let's break down that 2.1 gigatons. Where does most of it come from within those three industries?
In 2030, cement is the biggest chunk. Around 12,277 megatons, maybe 60% of that industrial potential. But its share actually drops by 2050, down to about 845 megatons or 34%. This study notes that cement emissions will become increasingly concentrated in developing regions like China, India, sub-Saharan Africa, basically wherever major infrastructure is still being built out.
Interesting. So who takes up the slack?
Waste incinerators. They're the second biggest in 2030, around 600 megatons, maybe 28%.
Right.
But their contribution grows a lot by 2050.
How much?
They become the largest industrial source, providing 56% of the industrial CO2 potential. And this supply becomes more spread out globally as more places adopt modern waste incineration.
And pulp and paper?
That's the smallest of the three, contributing a pretty stable 230, 250 megatons throughout the period, mostly concentrated in places with big forestry sectors, the Americas, Northern Europe.
So these industrial sources are key, especially at the start. But there are caveats, right? Assumptions made in the study.
Yeah, a couple of important ones. It assumes a pretty high capture efficiency, 87% from the exhaust streams. That's optimistic, but potentially doable. It also assumes a 70% maximum utilization potential for that captured CO2, basically acknowledging that you won't always have a CO2 user right next door to the CO2 source. Perfect geographic matching is tricky.
And it doesn't factor in the cost or logistics of moving CO2 around between regions?
Not in its main supply figures, no. That's a whole other layer of complexity and cost pipelines, ships, etc., that would need to be built out.
Okay, so industrial point sources give us a strong start, but clearly with demand hitting 6.1 gigatons by 2050 and these sources topping out around 2.5 gigatons total potential, there's a gap.
A big gap.
And this is where the technology that gets a lot of headlines comes in. Direct air capture, DAC.
Exactly. DAC is the necessary next step, according to this analysis. While those industrial sources are vital early movers, they just can't keep up with that skyrocketing demand curve mid-century.
So how big a role does DTA play by 2050 in this study's projections?
It becomes dominant. By 2050, DC is projected to supply the majority of the CO2 needed, about 3.8 gigatons per year.
Wow, 3.8 out of 6.1 gigatons? That's over 60%.
Yeah, a whopping 63% of the total global demand for CO2 as a raw material. It completely flips the script from the early reliance on industrial sources.
Can you trace that transition for us? How does the balance shift from industry to DC over time?
Sure. So 2030, as we said, point sources are doing almost all the work, over 90%.
Yeah.
By 2040, DC starts making a real impact, especially in certain regions. The study highlights places like parts of Russia, South Korea, Norway, Belgium, the Netherlands as early adopters or places where DC becomes significant.
Why those places specifically? Maybe high renewable energy potential or specific industrial needs?
Likely a combination of factors,
Yeah.
policy support, energy costs, existing industry, maybe fewer accessible point sources relative to demand. Then by 2050, the picture is clear. Most of the world relies mainly on DCCU direct air capture and utilization.
But with some exceptions.
Yeah, exceptions remain. Think Northern Europe with its strong pulp and paper industry providing bio-CO2, or maybe some sub-Saharan African nations where the overall CO2 demand is lower relative to their growing cement industry emissions. But globally, DDAGI takes the lead.
What about the cost difference? You capture CO2 from a cement plant flue gas where it's concentrated versus plucking molecules out of thin air. Days must be more expensive.
It is projected to be. This study estimates industrial capture costs around 12 to 25 euros per ton of CO2 by 2050. Day costs are projected higher, maybe 38 to 71 euros per ton by then. Costs are expected to come down for both, but daily remains pricier.
So do they compete, or is it just using the cheap stuff first?
The study models it more like the latter. It assumes no direct competition. Basically, use the cheaper industrial point source CO2 first, wherever it's available and matches demand. DAG then comes in to fill the remaining gap.
Especially in places without those big industrial sources nearby.
Exactly. Or in places with super cheap renewable electricity, which could make DAC more economically viable even if the capture itself is pricier. That location flexibility is DC's superpower.
Right, that flexibility seems key. You don't need to be near a cement plant.
Precisely. You can, theoretically, build a DAGS facility anywhere you have land, renewable energy, and maybe storage or utilization infrastructure. It decouples CO2 supply from industrial locations.
Which avoids potentially needing thousands of kilometers of CO2 pipelines in some cases.
It definitely helps with that challenge, yes. It offers a more decentralized path for sourcing carbon, potentially allowing e-fuel production closer to ports, airports, or renewable energy hubs.
Okay, let's zoom out again. We're talking about capturing and utilizing over 6 gigatons of CO2 a year. Producing the e-fuels and chemicals from that, that's going to need a staggering amount of energy, right?
Oh, absolutely. It's incredibly energy intensive. There's no getting around that.
Yeah.
This study puts the global electricity demand for synthesizing all these e-fuels and e-chemicals at around 58,000 terawatt hours by 2050.
58,000 TWH. How does that compare to today's global electricity consumption?
Well, current global electricity consumption is roughly 27,000 TWH.
Yeah.
So we're talking about needing more than double today's entire global electricity generation just for making these e-fuels and e-chemicals.
Wow. That really underscores the need for that 100% renewable energy system assumption.
It's fundamental. You absolutely cannot power this with fossil fuels. That would defeat the entire purpose. It requires a monumental build-out of solar, wind, geothermal, you name it, on a scale we haven't seen before. The study notes e-methanol and synthetic fuels made via the Fischer-Tropsch process are particularly energy hungry.
But if we can achieve that massive renewable energy scale up, the climate payoff is equally massive.
Immense. This is direct climate action. The study calculates the annually avoided CO2 emissions, meaning emissions that would have happened if we'd used fossil fuels instead, growing from about 1.2 gigatons in 2030 to over 12 gigatons in 2050.
12 gigatons avoided per year by 2050.
Yes. And cumulatively, between 2030 and 2050, the avoided emissions add up to something like 131 gigatons of CO2. That's a huge chunk of avoided warming. It's turning CO2 from just a pollutant into part of the solution cycle.
Are the economics starting to line up? Are there market signals pushing this forward?
They're definitely starting to emerge. You've got more and more carbon pricing schemes popping up globally. What was it, 68 of them back in 2022?
Covering almost a quarter of global emissions.
Right. That puts a direct cost on emitting CO2, which makes capturing and using it, or using fuels made from it, more attractive. Plus, let's face it, fossil fuel prices are volatile and generally expected to rise in the long run, especially with climate policies. That makes these synthetic alternatives look increasingly competitive.
It sounds like there could be some interesting shifts in global trade and industrial geography, too.
For sure. Regions that have both good access to those unavoidable industrial CO2 sources and high demand for the e-fuels and chemicals could become major production hubs. The study points to places like Europe, Northeast Asia, North America.
And you mentioned sub-Saharan Africa earlier.
Yes, interestingly, the study suggests sub-Saharan Africa could become a significant exporter of these products. Why? Because of its growing cement industry, providing a large CO2 source, potentially combined with excellent renewable energy resources. That could totally redraw energy and chemical trade maps.
Of course, this is a model, a projection. It comes with uncertainties and challenges. What are some of the big ones the study flags?
Well, a major one is that the demand projections rely on a best policy scenario. That means it assumes governments actually implement strong climate policies needed to hit the 1.5 degrees C goal, widespread carbon pricing, rapid renewable deployment. If policies lag, the demand might not materialize as quickly.
So political will is key.
Absolutely. And then there's the practical challenge of matching supply and demand geographically. We talked about DAXI's flexibility, but you still need to move either the CO2, the hydrogen, which is also needed for synthesis, or the final e-fuel product.
Transporting CO2 isn't trivial.
No. Pipelines are mature technology. The U.S. has thousands of kilometers already, but building them out globally is a massive infrastructure project. The study does note, interestingly, that transporting CO2 by pipeline is significantly cheaper on a per-ton basis than transporting hydrogen. That's an important factor for system design, but still costly.
And this whole discussion is about using the CO2. But DASH also opens up another possibilities, doesn't it? Just locking the CO2 away.
Exactly. This study focuses on DICU utilization, but there's also DICCS direct air capture and storage, permanently removing CO2 from the atmosphere and storing it underground.
Which we'd need for net negative emissions, actually reversing the buildup.
Precisely. Many climate pathways suggest we'll need large-scale CO2 removal later this century to get back to safer atmospheric concentrations. Some related research estimates we might need, get this, nearly 45 gigatons of annual DASI capacity by 2100, mostly for storage, to reach what they call a truly sustainable civilization. So utilization is one key part, but permanent removal is likely the other side of the DASCO coin.
Okay, let's try and wrap this up for you. What we've journeyed through today, based on this detailed study, is a really profound potential shift. Carbon dioxide moving from public enemy number one
to a valuable, essential raw material for defossilizing huge parts of our economy. It's about rethinking waste.
And it takes a two-pronged approach to get the carbon needed. First, tapping into those sustainable, unavoidable CO2 streams from industries like cement, pulp and paper, and waste incineration. They're the crucial first movers.
But then, the indispensable heavy lifter becomes direct air capture. D-Day is what allows this vision to scale globally, providing carbon flexibly wherever we have clean energy.
So this isn't just a tech story. It's about reshaping economies, infrastructure, global trade. It demands supportive policies, massive investment, and a new way of thinking about industrial processes. For you, understanding these dynamics isn't just academic. It gives you a lens on the future of energy, transport, materials, maybe even your own industry or investments. What does a world running on captured carbon truly look like? And what role might you play in getting there? That's something to really chew on.
Thank you for joining us on this deep dive, exploring the potential of carbon utilization, grounded in the research titled global demand analysis for carbon dioxide as raw material from key industrial sources, and direct air capture to produce renewable electricity-based fuels and chemicals.
Until next time.